Okay, this is section 4.2, graphing polynomial functions. Okay, so we're going to talk about the graph. It's not really complicated stuff because really at this point, these functions, their graphs are so complex that all that we can really do by hand is just get a feel for what the graph is doing. Okay, so we're not actually going to graph them precisely. We're going to just discuss certain aspects of the graph, get a general picture of what they look like and what they're doing. Okay, so a couple of things to start off with. In the section 4.1, we talked about degrees, the leading term, and all of that stuff. Okay, this is really going to focus on the degree. Remember, the degree is the highest exponent. Okay, the highest exponent. So I'll write that down. The degree is the highest exponent. And I'm going to just say n is our degree for now. Okay, the number n, whatever that happens to be. So 10, 4, doesn't matter. Okay, so for the graph, if we're talking about the graph, okay, from the degree, you can determine the number of real zeros, at least the maximum number of real zeros, and the maximum number of turning points. Okay, so let me show you what that looks like on the graph after I fix that G there. Turning points. Okay, so the degree will tell you, let's say you have something like this. This graph right here is a cubic function, right? This is x cubed or something like that. Okay, it could be 3x cubed plus 2x, it could be something. Don't really care. Anyway, this is x cubed. It looks like this. Okay, the real zeros are the same thing as the x-intercepts, okay? Or at least they tell you where the x-intercepts are. So you can say real zeros and x-intercepts are kind of the same thing. Of course, a zero is a number that you plug into a function that will make the function equal 0. Okay, that's a 0 of a function. The x-intercept is where is that located on the graph? The x value, right? The number, comma 0. Okay, so that's the difference between an x-intercept and a 0. The 0 is the actual number you plug in. Okay, the x-intercept is the point. All right, so anyway, that's not hard to find. So the real zeros and the x-intercepts are these points here, right? Okay. Turning points would be where the graph switches from going up to going down. So in other words, right here. Before that point, it was going up. After that point, it's going down, right? So it's a turning point. There's another one here. Okay, notice there are 3 zeros. There are 3 x-intercepts. And there are 2 turning points. Okay, it's kind of like there's a turning point between each of the x-intercepts. Okay? If you picture it like that, then you should be able to remember that the maximum, I should put maximum, number of real zeros that there could be less than this, but most of the time this will line up, is whatever the degree is. Okay, and then the maximum number of turning points would be 1 less than the degree. And while we're at it, let's throw in the max number of x-intercepts would be n as well, right? Because these two are basically the same thing. Okay, so let's do an example. Maybe simplify this a little bit. So example 1, we have this function here. Okay, and I want to determine, for part A, the maximum number of real zeros. Now, again, these are the real zeros. We're not talking about imaginary zeros. That could be, those could exist too. So that's why we say the maximum number of real zeros. It's possible that you have some real zeros and then some of them are imaginary, okay? So maximum number, if they're all real zeros, that'll be the max number. Okay, maximum number of x-intercepts. I guess I'll write out the word here. And the maximum number of turning points. Okay, so that's a lot of writing. The question actually was longer than working it out, because once I identify the degree, which is 6, right, the highest exponent, I know that the maximum number of real zeros is 6, the degree. The maximum number of x-intercepts will be the same number since they're basically the same thing. And the maximum number of turning points will be one less than those, which is 5. That's it, right? That's all I'm asking here. So from that, you can kind of picture what the graph looks like, right? It crosses the x-axis 6 times, and it turns 5 times at the most. Okay, what does that look like? So negative leading coefficient, so it's going to go down to the right. Oh wait, no, I'm looking at the wrong one. Here we go. The degree is even, so the left side will be even with the right side. They'll match up. Okay, and then maximum number of x-intercepts is 6, so I should cross the x-axis 6 times. 1, 2, 3, 4, 5, 6. There we go. Right, 1, 2, 3, 4, 5, 6. And the turning points. 1, 2, 3, 4, 5. The graph looks something like that. Okay. All right. Let's do another example. We didn't have to sketch the graph for that one, but, you know, why not? So example 2, we have f of x is equal to 1/4 x cubed plus 2x squared. That's all we're going to do there. A, B, and C, maximum number of real zeros. Maximum number, I'm just going to abbreviate or shorten that. Real zeros, what we're talking about here. Maximum number of real zeros. Maximum number of x-intercepts. And the maximum number of turning points. All right, and so the degree, highest exponent is 3. So 3 real zeros, 3 x-intercepts, 1 less than 3 is 2, 2 turning points. Easy enough, right? Example 3. Okay, so example 3, we're going to have a function, and I want to sketch the graph using all of that information. Okay, and this is going to be a wild-looking one here. I do want to point out, though, remember, however long this problem looks, most of it is irrelevant, right? All I care about is the leading term. This I don't care too much about. I might care about the constant term because there is something special about the constant term. Maybe you remember back from linear functions when we would write it out like this. Y equals mx plus b, or f of x equals mx plus b. The y-intercept was 0b. That's actually true for all polynomial functions. The constant term is the y-intercept, okay? Or at least it's the y value of the y-intercept. Okay, so I want to use all that information that I just said to sketch the graph. So things that I know. The maximum number of real zeros is going to be 6. The maximum number of, and you know, the same thing is true about x-intercepts. The number of turning points, TP, not toilet paper, but turning points, would be 5. Okay? From the leading term, I can see the leading coefficient is negative 0.5. In other words, it's negative. So as far as the end behavior is concerned, right, from section 4.1, it's going to go down to the right. Right? Negative means the right side goes down. The degree is 6, which is an even number. Remember, if the degree is even, the left side will be even with or match the right side, so it's going to be down as well. Okay, and then I have the y-intercept is negative 3, so we're going to say 0, negative 3. Okay, so now, put all that together. It goes down this way. It goes down that way. It crosses at 0, negative 3. And it's going to cross the x-axis 6 times or less. 1, 2, 3, 4, 5, 6. There we go. It's kind of ugly, but whatever. Okay, so it looks something like that. Here we go. Notice it crossed 1, 2, 3, 4, 5, 6 times. And count the turning points. 1, 2, 3, 4, 5. That's my rough sketch of the graph. Okay, let's do one more of those. Negative 1/3 x cubed minus 4x squared plus 6x plus 42, not 12, 42. Okay, just doing a sketch of the graph. Okay, so real zeros are x-intercepts. We're going to have 3 of those at most. The y-intercept is going to be 0, 42. Number of turning points would be 2. Okay, and then the end behavior. So end behavior, remember, leading coefficient is negative, so it's going to go down to the right. Degree is odd, so the left side will be at odds with the right side. It's going to go up. 0.42, we'll just say that's 0.42. It's way up there. Okay, and let's cross the x-axis 3 times. So we're going to have 1, 2, 3. All right, that's a good one right there, right? 1, 2, 3. And the turning points, 1, 2. Okay, there we go. So that's going to be the first part of section 4.2.